It is late autumn, 1944, on a rutted, rain-soaked road in eastern France. An American reconnaissance patrol creeps forward through the morning mist. Inside, the radios have been violently smashed with heavy tools. More deliberately, a thermite grenade has been dropped into the open breach. Within seconds, the entire final drive assembly chewed itself into a useless mess of seized metal and jagged shrapnel. The track connected to the shattered drive would stop dead. The tank would lurch violently and settle into the mud. No matter how hard the driver revved the engine, the power could no longer reach the earth. The machine was paralyzed. This was a fundamentally different crisis than a thrown track or a shattered road wheel. When a tank breaks a track link, the crew can climb out, retrieve their tools, and use sledgehammers, pry bars, and replacement pins to repair the damage. It is exhausting, dangerous work, but it can be resolved by the men on the ground. A shattered final drive offered no such hope. The gears were heavy internal components, sealed securely behind bolted armor and thick structural casings. A stranded five-man crew could not reach the broken machinery, let alone repair or replace it under fire. In a fraction of a second, the heavily armed predator of the battlefield was reduced to a stationary steel pillbox. The sloped armor and the long gun still functioned, but a tank that cannot maneuver is ultimately just a target waiting to be outflanked by infantry or destroyed by artillery. The crew was helpless to move their own vehicle. They had to call for a rescue of the main gun. The extreme heat has melted the steel, welding the firing mechanism shut in a pool of hardened, immovable slag. But that necessity triggered the next layer of the hidden problem. The broken metal teeth inside the hull did not just stop one tank. They created an immense logistical anchor. How exactly does an army drag a paralyzed 45-ton fortress out of the mud? When the grinding metal noise finally ceased and the Panther sat paralyzed in the mud, the immediate problem was no longer tactical, it was physical. The tank was now 45 tons of dead weight. Worse, because the final drive was completely seized, the tracks could not roll freely. The crew was not just sitting inside a heavy vehicle, they were sitting inside a massive steel anchor dropped into the earth. Dragging that anchor back to a field workshop required a staggering amount of kinetic force. For lighter, earlier machines like the Panzer III or IV, the German army relied on standard towing equipment, primarily the heavy 18-ton half-track. But the Panther was an entirely different class of weight. A single heavy half-track did not possess the raw torque or traction to pull a paralyzed Panther out of deep mud or up a forested incline. To move just one broken tank, a recovery crew had to link two, and sometimes three, of these massive half-tracks together in a single chain. This created an incredibly clumsy and dangerous steel train. 3 separate drivers had to synchronize their clutches, gears, and acceleration perfectly. The German crew destroyed their own weapon, climbed out, and walked away. To the Allied soldiers staring at the abandoned giant, if one driver applied too much power while another hesitated, the thick steel towing cables would snap under the immense tension, whipping back with enough force to tear through metal and bone. If the road was narrow, bordered by dense forests or steep ditches, maneuvering this long chain of vehicles to pull the dead tank away from the front line was often geometrically impossible. The German military recognized this logistical nightmare and attempted to solve it by building the Panther. This was a dedicated heavy recovery vehicle constructed on a turretless Panther chassis, equipped with a massive internal winch and a heavy steel earth spade to anchor it during a pull. It was a mechanical necessity, highly capable of retrieving the heavy armor. But the Panther introduced a painful mathematical compromise. To build one, a factory had to divert a chassis away from combat production. Every recovery vehicle built meant one less lethal 75mm gun rolling onto the battlefield. Furthermore, there were never nearly enough of them. A heavy tank battalion might be issued only a handful of Panthers to support dozens of frontline vehicles. When the final drives began to shatter in the field, they rarely failed one at a time. The fragile, straight-cut spur gears. This scene contradicts the basic laws of armored warfare. A tank is a mobile fortress. You do not abandon a fortress unless were a universal industrial flaw, meaning an entire company of Panthers, subjected to the same rough terrain, thick mud, or steep inclines, would often suffer multiple failures simultaneously. The recovery network would instantly buckle, while the specialized crews were fighting to winch one tank out of a ditch under the cover of darkness. 3 more would radio for a tow from a few miles down the road. This cascading failure transformed the maintenance battalion from a support unit into a desperate, overworked triage center. Highly trained mechanics spent their days and nights wrestling with massive field hoists, unbolting heavy armor plates, and struggling to replace shattered gear casings in the freezing rain. Precious fuel was burned not by tanks advancing on the enemy, but by recovery engines dragging their own broken forces backward. A single, shattered final drive did not merely subtract one tank from the roster. It acted as an operational black hole. It consumed time, specialized vehicles, technical labor, and crowded the road network. The invisible mechanical flaw had successfully paralyzed the German support chain, leaving field commanders looking at an armored force that was bleeding out its own strength, just trying to maneuver. This compounding maintenance debt fundamentally altered the reality of the war room. The question for German generals was no longer, the enemy blasts you out of it. The Panther was widely considered the apex predator of the European theater. Just where to deploy their armor, but how to plan an offensive when the simple act of driving to the staging ground destroyed the army. Inside a damp, canvas-roofed command post behind the front lines, a German staff officer stands over a folding wooden table. He is studying a map marked with blue and red grease pencils. An Allied column has broken through the defensive line 50 miles to the west. The officer has a full battalion of Panther tanks waiting in reserve. In standard military logic, the tactical solution is obvious. You start the engines, drive the 50 miles, and crush the breakthrough. But the officer hesitates. For a Panther unit, a 50-mile road march is not a simple deployment. It is a mathematical crisis. This hesitation was the direct result of the road march tax. In armored warfare, operational mobility is survival. The ability to shift heavy forces laterally across a theater, rushing them to plug a sudden gap or exploit a retreating enemy, is what allows generals to control the pace of a campaign. But German commanders found themselves fighting a constant, losing battle against their own odometers. The lifespan of the Panther's final drive was terrifyingly short. Technical reports trickling back to the maintenance depots revealed a grim reality. On paper, it was a masterpiece of lethal geometry and thick frontal plating. German crews were rigorously trained to leverage this superior machinery. The fragile, straight-cut spur gears often began to fail after just 150 kilometers of normal driving. If the route involved steep gradients, deep mud, or required constant pivoting through the narrow, twisting streets of European villages, that mechanical lifespan plummeted even further. Because of this structural fragility, issuing a movement order carried a guaranteed cost. If a commander ordered 40 Panthers to drive 50 miles to a staging area, he knew with absolute certainty that not all 40 would arrive. A predictable percentage would suffer catastrophic gear failure along the route. By the time the column reached the assembly point to actually begin the attack, the unit would have already taken significant casualties. The armor was being defeated by the friction of the road, completely independent of enemy action. This crippling reality forced a profound shift in how the German military could wage war. Their armored reserves lost the ability to act as a fluid, reactive fire brigade. A general could no longer authorize deep, sweeping flanking maneuvers or complex, multi-stage counterattacks. The mechanical attrition of the march would bleed his combat strength dry before his tanks ever fired their heavy guns. The armor became inherently rigid. To preserve the brittle metal teeth inside the lower hulls, the tanks had to be hoarded, using the tank's heavy armor to hold ground and bleed the advancing allies. Voluntarily surrendering an intact vehicle without firing a single defensive, they were kept perfectly still in camouflaged, static positions, waiting as long as possible for the battle to come to them. The strategic contrast was stark. The Allies, particularly the Americans operating the mechanically reliable Sherman, could drive for days. An American armored division could fight a skirmish in the morning, drive 40 miles in the afternoon, and assault a new position by dusk. They fought a war of relentless motion. The Germans were shackled by their own machinery, forced to fight a war of strict conservation. Every revolution of the drive sprocket was carefully measured. Every mile traveled was deducted from the short lifespan of the tank. But an army cannot defend a collapsing continent by remaining entirely static. Eventually, the heavy armor had to be moved to meet advancing Allied spearheads or to mount desperate counteroffensives. If the simple act of driving the machines under their own power destroyed them, the military needed an alternative method to deliver their firepower. They had to find a way to move 45-ton tanks without ever turning the engines on. Deep in the German rear, a massive steam locomotive idles beneath the steel girders of a marshalling yard. Behind it stretches a long line of heavy flat cars. On these reinforced wooden decks sit the Panthers, their engines completely silent, their gun barrels clamped tight into travel locks. Shot made no tactical sense. But as the Allied armies pushed deeper toward the German border, they realized this was not an isolated panic. This was the military solution to the road march tax, to prevent the fragile double spur gears from tearing themselves apart. On the way to the battlefield, commanders decided the tanks should not drive at all. They would be carried. The German railway network became the mechanical life support system for the armored divisions. By loading the heavy vehicles onto trains, the military could move its lethal firepower hundreds of miles across the theater without putting a single revolution of stress on the final drives. But turning a frontline combat vehicle into freight carried a severe logistical cost. Loading a 45-ton Panther was not a rapid maneuver. It required specialized heavy-duty flat cars capable of bearing the immense weight. It demanded concrete loading ramps that would not collapse under the steel tracks. The process was slow, methodical, and required highly coordinated railway schedules. This reliance on the rails fundamentally altered the geometry of German defense. The armor was now physically tethered to the train tracks. A Panzer division could only deploy as close to the front as the nearest functioning railhead would allow. If a Soviet or American breakthrough occurred in a sector lacking deep rail infrastructure, the tanks had to be unloaded miles away and forced to drive the remaining distance. Every mile between the offloading ramp, they kept finding them. Dozens, then hundreds, of Panthers were discovered sitting silently on roadsides, stranded at muddy crossroads, and the actual fighting chipped away at the narrow lifespan of the gear teeth. Commanders found themselves planning armored counterattacks, based not just on the best terrain for their guns, but on the proximity of the closest train station. For a time, the network functioned. The heavy armor was preserved for the moment of contact, but a military strategy dependent on fixed steel rails shares a fatal flaw with the final drive itself. It cannot bend, and it is highly vulnerable to friction from the outside. By the summer of 1944, The skies over Europe belonged almost entirely to the Allies. American and British tactical aircraft roamed the road and rail networks, hunting for any sign of movement. Allied pilots did not need to penetrate the Panther's heavy, sloped armor to neutralize it. They simply destroyed the infrastructure keeping it alive. Fighter bombers shattered railway bridges, cratered marshalling yards, and strafed the heavy locomotives. The intricate system of moving armor by train began to violently collapse. A train carrying a battalion of Panthers might find its route, suddenly severed by a destroyed bridge 50 miles from the intended destination. The train could go no further. The concrete offloading ramps were miles away. The crews had no choice but to hastily build earthen ramps, unchain their vehicles, and stalled at the bottoms of shallow hills. Allied intelligence officers initially assumed an obvious culprit: fuel starvation, German supply lines, and start the engines. To reach the desperate infantry begging for support at the front line, the Panthers now had to drive across the exact rough terrain, steep hills, and deep mud they had been trying to avoid. The road march tax was instantly reinstated. The final drives began to snap long before the tanks ever saw the enemy. Moving toward the front under these conditions was a mechanical nightmare. But an advancing army at least controls the ground behind it, allowing heavy recovery vehicles to eventually reach the broken machines. The true cost of the industrial compromise had not yet been fully realized. The ultimate test of this fragile system would not come during an attack. It would come when the rail lines were severed, the front line collapsed, and the heavy armor was forced to do the one thing it mechanically could not survive. The front line has broken. It is a chaotic, freezing night, and a German armored column is retreating down a rutted dirt road. In the middle of the convoy, a Panther driver attempts to navigate a deep, waterlogged crater. He shifts gears, engages the clutch, and pushes the throttle. Beneath his feet, there is a sharp, metallic crack, followed immediately by the sickening sound of steel chewing itself apart. The right track locks, the men staying low in the muddy ditches. Around a bend, they freeze. Sitting sideways across the narrow lane, were under constant aerial bombardment, and gasoline was critically scarce. But when military engineers dipped measuring rods into the fuel tanks of these percent, the engine roars uselessly, spinning raw power into a shattered casing. The 45-ton vehicle sinks slightly into the mud and stops. In a successful offensive, this is a severe delay. The crew would shut down the engine, grab their rifles, and wait for a heavy recovery unit to drag the machine back to a secure field workshop. But in a fluid, collapsing campaign, the geometry of the battlefield is inverted. The enemy is advancing rapidly behind them. The ground the tank sits on will belong to the Americans or the Soviets within the hour. The commander pushes open his top hatch and looks down the dark road. There is no Berger Panther coming. The heavy half-tracks are already choked with desperate infantry and towing essential artillery pieces, crawling away as fast as they can. Even if a recovery vehicle were present, maneuvering it into position on a narrow, congested escape route, while under artillery fire, is physically impossible. The strict mechanical support network required to keep the Panther alive has completely disintegrated. The crew is forced to face a devastating reality. Because they cannot move the tank, and they cannot tow the tank, they must destroy the tank. A minor mechanical failure, the shearing of a few low-quality steel teeth on a straight-cut spur gear, has just escalated into the total, irreversible loss of abandoned machines. They often found them half full. There were heavy armor-piercing shells still secured in the ready racks. One of the most lethal weapons in the German arsenal. This was the hidden attrition that bled the Panzer divisions dry. As the German military was forced into continuous retreat across Europe, the vulnerability of the final drives exacted a catastrophic toll. When post-war analysts examined the staggering number of Panthers lost during the late stages of the war, the surface statistics were highly deceptive. The vast majority of these machines were not outflanked by American Shermans or overwhelmed by Soviet T-34s. They were not struck by aircraft or obliterated by artillery. They simply broke down on a muddy road, on a steep hill, or at a blocked intersection, and were subsequently blown apart by their own crews. The men who operated these tanks were rigorously trained to fight. Instead, they became executioners of their own machines. They learned exactly where to place thermite charges in the gun breech to melt the firing block. They learned how to swing heavy tools into the fragile radio sets. They learned how to drop explosives into the engine compartment, to crack the cast iron block, ensuring that an advancing enemy could not salvage the pristine sloped armor or the terrifying 75mm gun. A weapon is designed to project power and protect its operators. But what is the true value of a fortress if its own weight guarantees its destruction? The tracks and suspension systems were fully tensioned and intact. The tank possessed everything it needed to fight, except the ability to move. The heavy armor and high-velocity gun provided localized tactical supremacy. If an Allied unit drove directly into its sights, the Panther almost always won. But warfare is not a series of isolated duels. It is a relentless, grinding test of endurance, logistics, and operational motion. The broken metal inside the hull forces a fundamental re-evaluation of armored superiority. How do we judge a machine that consistently wins the firefight but systematically loses the campaign? The American infantrymen shivering in the freezing drizzle on that French road did not know about industrial quotas, planetary gears, or the metallurgy of straight-cut steel teeth. They only knew what they saw: a 45-ton apex predator, armed with a gun that could have torn their patrol to pieces from a mile away, sitting silently in the mud. The mystery of the pristine, abandoned Panther was never truly about the vehicle's combat capability. When it reached the battlefield and faced the enemy, it performed exactly as its designers promised. But the terrifying sloped armor and the high-velocity gun were only the visible tip of an invisible system, and that system was broken at its core. The German military had convinced itself that tactical superiority would win the war, measuring ultimate success in muzzle velocity, armor thickness, and battlefield kill ratios. They built a machine optimized to destroy other machines in direct combat. But they fundamentally misunderstood the scale of the conflict they were fighting. Something inside the hull had broken so catastrophically and so irreversibly that an experienced five-man crew decided their only remaining option was. World War II was not a series of isolated duels on flat, paved test tracks. It was a grinding, continent-wide war of logistics, endurance, and operational mobility. A weapon is only as lethal as the supply chain and the maintenance network keeping it alive. Because German factories lacked the specialized machinery and high-grade alloys to build robust final drives, they sent their crews into combat with a fatal compromise. The Panther was a masterpiece of lethal geometry, balanced precariously on a handful of brittle gear teeth. It was a devastating sword with a shattered hilt. That single point of failure radiated outward, poisoning every level of German operational planning. It paralyzed the heavy tanks on the road march, taxing the army before the battle even began. It overloaded the frantic, under-equipped maintenance battalions. It tied the armored reserves to the fragile railway network, stripping commanders of their ability to maneuver. And when the front lines finally broke and the retreat began, it forced experienced tank crews to destroy their own irreplaceable machines, simply because they could not pull them out of a ditch. Behind the fearsome silhouette of the Panther, there is a distinctly human reality of wasted effort and shattered morale. The machine was the product of immense, grueling labor, to sabotage their own vehicle and flee on foot. To understand why a military desperate for firepower would surrender its most conscripted factory workers spent thousands of hours welding the thick hull plates in unheated assembly plants under the constant threat of bomber raids. Munitions workers produced perfectly balanced, high-velocity shells. Fuel was meticulously hoarded and transported under the cover of darkness. Elite crews spent months training to master the complex gunnery optics. Yet, all of that human effort, all of that fuel, steel, and training could be instantly erased by a single patch of deep mud and the snap of cheap metal. We remember the imposing armor, but we overlook the exhausted mechanics working through the night in freezing rain, desperately trying to unbolt a seized gear casing with hand tools and improvised field hoists. We forget the terrified driver, gripping the steering levers, knowing that a slight miscalculation on a steep incline could instantly paralyze his crew and leave them stranded in hostile territory. The Pristine tank left on the side of the road was not defeated by Allied firepower. It was defeated by the earth beneath its tracks and the suffocating industrial reality that built it. The men who dropped the thermite grenade into the breach and walked away into the forest understood the final, unforgiving verdict of the war. Formidable weapon to a muddy road. We must look past the heavy armor and the lethal gun. We have to examine. A fortress is useless if it cannot move, and the ultimate weapon of the battlefield was ultimately killed from the inside. The invisible violence tearing the machine apart from the inside, long before the enemy ever came into view. To the men staring down the barrel of a Panther, the idea that the machine possessed a fatal weakness seemed absurd. By the late summer of 1944, the Panther had earned a terrifying reputation. If you asked an American Sherman crew or a British Churchill gunner what made the German tank so dangerous, they would not talk about logistics or gear ratios. Is a German Panzerkampfwagen V, better known as the Panther. It is 45 tons of heavily sloped, camouflage-painted steel. They would talk about geometry and velocity. When the Panther was conceived after the shock of encountering Soviet armor in 1941, German engineers were given a clear mandate. They needed a vehicle that could dominate any frontal engagement. They delivered a machine wrapped in 80 millimeters of steel on its upper glacis plate. But the true defensive strength was not just the thickness of the metal. It was the angle. Sloped backward at 55 degrees, that steel effectively doubled in line-of-sight thickness. When an Allied 75mm armor-piercing round struck the front of a Panther, it rarely bit into the metal. The slope deflected the kinetic energy, sending the shattered American or British shell spinning harmlessly into the sky. Behind that impenetrable wall of steel sat the tank's main armament. The Kabuki 42 75mm gun was uncommonly long, extending far beyond the front of the hull. That barrel length allowed expanding propellant gases more time to accelerate the projectile. When a German gunner stepped on the firing pedal, the shell exited the muzzle at over 3,000 feet per second. It flew on a trajectory so flat and struck with such devastating kinetic force that it could punch cleanly through. Its long, high-velocity 75mm gun is an undisputed terror, capable of punching through an Allied Sherman tank from far beyond the Americans' effective range. The thickest armor of an advancing Sherman from more than a mile away. In a static fight, parked at the end of a long French road or looking down a wide European valley, the Panther was the master of the battlefield. A single platoon of these tanks, positioned carefully behind a ridgeline or concealed in the ruins of a village, could shatter an entire Allied armored company. The German crews knew this. They trusted the math of their armor and the reach of their guns. As long as the enemy remained in front of them, They felt virtually untouchable. This was the illusion of the apex predator. War, however, is not fought on a static firing range. The tactical superiority of the Panther relied entirely on a specific condition. The tank had to be facing the threat, and it had to be waiting. But battlefields are fluid, front lines collapse. Infantry requires sudden fire support. On the opposite side of a river, enemy armored columns break through the flanks, demanding immediate counterattacks. A tank is fundamentally not a bunker. It is a weapon of maneuver, and its survival depends on its ability. The infantrymen wait in silence, expecting the violent crack of a coaxial machine gun or the sudden, deafening roar of the main gun. To traverse rough terrain, climb muddy ridges, and pivot rapidly to face new threats. To perform those maneuvers, the massive horsepower of the Panther's engine had to be translated into physical motion. The engine alone does not turn the tracks. The power must travel through a transmission, into a steering mechanism, and finally outward to the heavy sprockets that pull the steel track links. This final transfer of power occurs in a component called a final drive. This is where the armor's geometry and the gun's velocity ceased to matter. The Panther was a masterpiece of lethal engineering on the outside. But deep inside its lower hull, buried beneath the thick steel plates and the crew compartment, a dark mechanical reality was waiting. The men inside the tank believed they were commanding an invincible fortress. They could not see the fragile industrial compromise preparing to snap beneath their feet. The power generated by the Panther's massive V12 engine had to go somewhere. It traveled forward from the rear of the hull, passed through a complex transmission, and finally reached the front drive sprockets. The crucial junction between the transmission and those heavy steel sprockets was the final drive housing. This was the mechanical bottleneck, the single point where raw engine revolutions were converted into the brute torque required to drag 45 tons of steel across the earth. But the forest remains quiet. The engine is dead. When the patrol finally maneuvers close enough to inspect the vehicle, in a vehicle of this immense weight, engineers usually rely on a planetary or epicyclic gear system. A planetary gear distributes the staggering rotational stress across multiple gear teeth simultaneously, much like planets orbiting a central sun. By spreading the physical load, it prevents any single point of metal from bearing the entire strain of the tank's momentum. It is a robust, highly resilient design capable of handling the extreme forces of a heavy armored vehicle, starting, stopping, and pivoting on rough ground. German engineers knew this. Their early blueprints intended for the Panther to utilize precisely this kind of durable system. But by the time the Panther entered mass production, the German industrial machine was suffocating. The Allied naval blockade and relentless strategic bombing campaigns had severely restricted access to critical raw materials. The high-grade steel alloys required to forge durable, shatter-resistant gears, specifically those hardened with nickel and molybdenum, were increasingly reserved for aircraft production or were simply unavailable. Worse than the metallurgical shortage was a silent manufacturing deficit. Cutting complex planetary gears required specialized, high-precision tools, such as sophisticated gear-cutting machines that could not be easily replaced once destroyed or worn out. The tension gives way to confusion. The tank has not been struck by artillery. There are no blackened scorch marks from aircraft rockets. Germany simply did not have enough of these precision machines left functioning to match the urgent, ever-increasing production quotas demanded by military leadership. Factories could roll out heavy exterior armor plates by the thousands, but they could not manufacture the intricate internal components required to make that armor move reliably. Faced with this insurmountable reality, the designers made a fatal compromise. Instead of the resilient planetary system, they installed a double spur gear mechanism inside the final drive housing. A straight-cut spur gear is fundamentally simple. It is easier to machine, requires less specialized tooling, and can be produced rapidly by less experienced factory labor. But it possesses a severe mechanical limitation. Instead of distributing the torque across a wide, interlocking surface area, a spur gear transfers the entire rotational force of the engine through just one or two metal teeth at any given microsecond. The engineers understood the grim math. They were taking a drive system structurally suited for a much lighter 20-ton machine, stripping it of its high-quality hardening alloys and forcing it to carry a 45-ton behemoth. The entire weight of the heavy sloped armor, the long 75mm gun, and the stacked ammunition racks ultimately rested on a handful of cheaply machined, no shattered tracks from mines, and no jagged entry holes from anti-tank rounds. The armored hide is entirely pristine, metal teeth. It was not a calculated design preference, it was an act of raw industrial desperation. On the smooth, paved test tracks near the assembly plants, the double spur gears held together long enough to pass final inspections. The tanks rolled out of the factory yards and were loaded onto flatbed rail cars, looking every bit the invincible predator the military desired. But a factory testing ground is an artificial environment. To understand why this single compromise eroded the operational strength of the German army, we have to look at the violent mechanical reality of the front line. The question was no longer if the final drives would fail, but what exactly would happen when those brittle teeth were tasked with forcing 45 tons of steel through the mud. Inside the cramped, deafening driver's compartment of a Panther, the physical reality of moving 45 tons of steel was an exercise in brute force and delicate timing. When a driver needed to navigate a steep, muddy incline or pivot the vehicle to face a new threat, he engaged the heavy steering levers and applied the throttle. Behind him, the massive Maybach V12 engine roared, generating nearly 700 horsepower. The noise was absolute, vibrating through the driver's metal seat and the thick steel floorboards. That raw power surged forward through the driveshaft and the complex transmission, seeking the ground. Yet the machine has been decisively killed. The heavy steel hatches are thrown wide open, exposing the dark interior to the freezing drizzle. But before it could turn the heavy exterior sprockets and propel the tracks, it had to pass through the final drive housing. Here, the brutal physics of the battlefield took over. As the steel track links bit deep into the wet earth, the mud and the incline fought back. With staggering frictional resistance, the engine pushed forward, the earth pushed back. All of that immense, competing kinetic energy collided at one precise location, the straight-cut spur gears. Because the gear teeth were not arranged in a resilient planetary design, the entire rotational torque of the engine and the crushing dead weight of the hull met on a surface area no larger than a few inches of metal. If the ground was too soft, if the incline was too steep, or if the driver engaged the clutch just a fraction of a second too abruptly, the strain exceeded the structural limits of the brittle, low-quality steel. The failure was instant and violent. Under the massive shear stress, one of the burdened gear teeth would simply snap off. Inside the hull, the crew would hear a sharp metallic crack echo over the roar of the engine, followed immediately by a horrific grinding noise. The severed chunk of steel did not just vanish. It fell directly into the tight, enclosed gear casing. As the remaining gear teeth continued to rotate, they caught the broken shard, crushing it against the casing walls and shearing off even more teeth in a catastrophic chain reaction.